Hi, thank you for the introduction. The purpose of the talk today is to tell you a bit about recent research, recent work that I've been focusing on with some colleagues. And this research is on formal methods and concurrency. And we will be looking at defining time-sensitive protocol and that satisfy certain properties and how to link then these protocols to implementations or, for what this talk is concerned, to abstractions of implementations. The problem that we are looking at is a distributed system. In this distributed system, we have independent programs that run and perform some tasks and interact by communicating via asynchronous message passing. So they exchange messages asynchronously. And we want these programs to follow specific protocols. And by protocol, I mean we want the programs to obey to some specific data structures of the messages they need to send and receive, but also they need to obey to some interaction structures, to some causality between interactions. Here you see a very simple example of an interaction between a client and a server. The server offers two options to the client, get or set, and depending on the option, you see that the client may need to send a string and receive an integer, or send a string and send an integer. So the interaction structures slightly change depending on the option chosen. So this is what I mean by interaction structure. And communication is not a core aspect of the functional paradigm, but it is useful in practice. And in fact, I think most functional programming languages have primitives for communication or libraries that address this aspect. So we will address the problem in two steps. First, we will be looking at protocols. We will be looking at defining communication protocols that are well structured. And when I say this, I implicitly say also that you may define protocols that are not well structured, so that are bad. And we want to avoid that. And we will do a bit of exercise while we survey a bit the literature of reasoning about interaction structures by using automata notation, which is a little bit more intuitive. And then we will look at another formalism that is called session types, that is related to automata, but offers a further advantage, other than formality, also the advantage of providing an easy link to implementations, that we will see. And then we will look at this part, so how to link this property to implementations in the second part of the talk. And I will describe a bit the literature that is on untimed interactions, and then I will also give you some hints of more recent research in which we also add time constraints to protocols, because we also want punctual interactions. So let's have a look at interaction structures. And we will do this by using a formalism called communicating automata. Communicating automata are like, or communicating finite state machines, they're also known by that name, are basically automata. You may find it familiar. They are communicating. Communicating means that in the edges, the label of the edges, the action of the edge, is a communication that can be a send action that is denoted with an exclamation mark, or a receive action that is denoted with a question mark. So you have this dual action, send and receive. Moreover, we are interested in asynchronous communication. So it's communication in which there is not a handshake between the sender and the receiver, but it is a two-step interaction in which you have first, well, let's see it here. You have first the sender on the left-hand side, the machine that sends the message A, and place it in a FIFO buffer. We will look at asynchronous communication on FIFO buffers. So A, you see that appeared in the buffer. At that point, the machine on the right could receive A, or also not now, could wait a little bit longer, and in that amount of time, the machine on the left may write an arbitrary number of B messages in the buffer. Okay? So this aspect, so asynchrony, makes reasoning on interaction structures complex, because you not only have possibly infinite traces of executions, but you also have a very large space of possible configuration of these buffers. And it is so complicated to reason on that many interesting properties like reachability are undecidable in the general scenario. I'll be more specific. A while ago, Gauda and others proved that even if you take just two machines, so a binary conversation, it is undecidable to know whether this, the system made by the composition of these two machines is free from deadlocks and unspecified receptions. Just to make sure we are all on the same page, by deadlock here I mean states, scenarios in which the machines in the system are not in a final state. In this case, they're all in the initial state, and none of them can proceed further. They're all trying to receive a message that is not there. Unspecified reception, now I slightly changed the example of the previous slide. The action on the left machine is a send action, so the machine can send the message, but the machine on the right waits for B, and so what is received is not what was expected. This reception is unspecified. So we cannot develop an algorithm decidable that that tells us if given generally a system, if it's free from deadlock and unspecified reception. And we can do nothing about that, the undecidability result, but we can restrict our focus to, well, a more narrow set of protocols. We can add some constraints to our protocols and see if we can get some interesting properties for free. And Gauda and others in the same work also give some positive results. They say, well, if you take two machines that satisfy three properties that we will see in a moment, then this will guarantee that your system is free from deadlocks and unspecified receptions. And let's have a look at these three properties so that we see what could go wrong with asynchronous communication. The first property, determinism. Two machines should be deterministic. A non-deterministic machine is a machine in which you have two edges that go out of a node that have the same action, but they go to two different states. And you can see that such a scenario can create confusion as to the state of the protocol in a distributed system. For example, if the machine on the left decides to send A and go on the state P2, the machine on the right receives A but doesn't know whether to go on Q1 or Q2. So you could have a confusing mismatching between the interactions in the system. So we don't want this, so we rule out all machines that are non-deterministic. Now we also rule out the machines that have mixed nodes. Mixed nodes are those nodes in which you have more outgoing edges, and some of them are send actions, some of them are receive actions. And similarly to the previous case, if you imagine a distributed system, you see that you could get confusion. You have the machine on the left that can either send or receive, the machine on the right can either send or receive. Communication is asynchronous, so there is not handshake. Both machines may decide to send and go to incompatible states. So we want to rule out also this scenario. The third property is compatibility. So we take a machine and we want another machine that is compatible for any possible execution trace of one machine. The other machine should be able to provide a dual trace, which is a trace that has exactly the same actions, but with the direction of the communication reversed, where there is a send, there should be a receive, and vice versa. So these three properties give us for free the deadlock freedom and freedom from unspecified receptions. Okay, let's come to session types now. Session types is a formalism that was introduced a bit later, and it has a different syntax. It allows you to define by construction correct protocol, so you don't have to worry about avoiding non-determinism and the other issues. And on top of that, it also has the advantage of providing this seamless link to programming languages that I've mentioned. And in fact, what I wanted to mention, the reason why there is a heart there, is that a relationship between session types and communicating automata has been established. So basically, session type can express the same as communicating automata that satisfies the three property, non-mixed state, compatibility, and determinism. And we will now go on talking about session types. So session types have a syntax that may look a bit less familiar. It's more like a process calculus syntax, but it means the same that we have seen for automata. The first, so a session type S could be a sending type that sends a message of type T, where T could be an integer, a string, or even another type. We have a receive action, the question mark of a type T, and then a continuation after receiving continues as S. The third type is a branching. It's a bit like the server giving a number of choices of behavior. So that construct corresponds in the automata world to a state where you have n outgoing edges, one with receiving a specific label, and the label are all distinct. And the other one is a selection, which is the dual action, the client that has a number of choices and chooses one of the labels. The last three are recursive definition, recursive call, and terminated type. And you can see that just by having this syntax, you have built in these properties that we were discussing for automata. We have non-determinism because the labels on branching and selection are all different. And we do not have mixed nodes because either you have branching or you have selection. You cannot mix and match. We also have something like compatibility. It's called duality in the session type world. You basically take a type and you reverse the actions. Let's have a look on how one can use session types. So on the left-hand side, we give a simple specification of a server that needs to be able to receive a message of type integer, and after that, will send a message of type string and terminate. The dual type is a client that sends an integer, and after that is ready to receive a string. Okay, here we are in the type realm. We are defining protocols. So what we can do after, we can implement these types. This is some pseudocode reminiscent of Haskell. See, for example, an implementation of the server reads on a channel A, a message that is assumed to be of type integer, and then depending on how big is X, will send back the specific string, small or big. And same for the client. And what session types allow to do, they are types. But they are types not only for the data types, but also for the behavior of the protocol. You can type check statically the program against the type to check that the interaction structures are preserved. And by doing this, since the protocols add interesting properties, we can also have the same properties down to programs. So we can guarantee that programs are free from unspecified receptions and free from deadlocks. Okay, this is literature on the untimed scenario, but what if we add time? So we have seen we can define protocols that are correct by definition, by using session types. Now we want to add time constraints, because, well, many protocols, many scenarios in the real world requires that they have some notion of deadline that we want to represent. Okay, time brings trouble. And a timed protocol, so if you just add arbitrary time constraints to a protocol, you may get a protocol that doesn't make sense, that is not feasible. The protocol that you have on the slide is a modification of the protocol we have seen before. And I have added time constraints, and I'm basically asking the server to be ready to receive an integer by 3 o'clock, and then reply with a string by 2 o'clock. You can imagine that if in some execution where the integer is received at 2:30, the server doesn't know how to proceed in a way that specifies the protocol. Okay? So this is a known problem, and it has been addressed by having some algorithm that checks well-formedness of a protocol, and again rules out all protocols that are not well-formed. There are several notions, several algorithms, but they all go along the lines, check that for every state in the protocol, that includes also the state of the clocks of the protocol, there is always a possible path forward. I didn't mention it, I hope it was clear that X is a clock that we use to define time constraints. And all these algorithms would agree, for example, that the protocol on the bottom here is well-formed. It is not equivalent to the one on the top, that's ruled out, but the one on the bottom is well-formed, and the only difference is that I have added this X after X is smaller than 3, which means reset X after receiving the message. So that X is set to 0, and then we can satisfy the next constraint. Okay, so let's assume from now on that the single protocols we are considering are well-formed. And let's look at the problem of compatibility, of duality. So in the untimed world, duality, so this relation between types where one is exactly as the other, but the directions of the interactions are reversed, characterize these well-behaved systems. Now we want to define a notion of timed asynchronous duality that give us the same than untimed duality. And this is a very nice notion of compatibility because it's very easy to derive. You just take a type, copy and paste, and just reverse the order of the interactions. So the most naive notion of timed duality that you can come up with is, well, take the untimed dual of a session types, and then you copy and paste the time constraints. This is what I've done there. I have just changed the name of the clocks, so S as the clock X, and its dual as the clock Y, to make it clear that every session type corresponds to a distributed node, and each has its own clocks. They don't have a global shared clock. That's a more realistic assumption. Okay, so does timed duality characterize well-behaved systems? Well, if we were in the synchronous scenario with handshake communication, yes, that's a simpler case, but asynchronous communication is tricky. And, well, I anticipate that we will find some troubles. But let's have a look at what is specifically the trouble. So while doing that, I also give you an overview of how the session types would behave, what behavior they actually characterize. So let's try to run these two session types. We put them in parallel with each other. On the bottom, you have the two clocks, X and Y. And on the right-hand side, you have the channel, the buffers for the communication from the dual of S to S and vice versa. Okay, we start. The first thing that should happen is that the dual of S needs to send an integer, but can do it at any time as long as Y is smaller than or equal to 1, so we can let some time elapse, okay? And the clocks are both updated. Time flows at the same pace for all the system, so the time progresses. And then the dual of S sends the integer is placed in the queue, And then what you see after is the remaining bits of interaction without the send of the integer. After that, it's S's turn to receive the integer, but this can be done at any time that satisfies the constraint x smaller than or equal to 1. So we can wait another 0.6, and now you see the clocks have different value as time proceeds because of this reset. And then S receives the message that is taken from the queue and resets the clock. Okay? And next is S's turn to send the string. And this can be done at any time as long as x is smaller than or equal to 2. So, well, S can wait until 2. And you see that now the time for the dual of S goes beyond the deadline. Okay? So, technically, what happens in the formal, what happens formally here is that the protocol gets stuck because we can't continue correctly, but in the real world, this is a protocol in which you would not be able to satisfy your own commitments, your own requirements. Okay? And we try to hack the definition of duality and change it in a way that it works, but we could not come out with anything better than, well, some algorithm that explores the spaces. But we wanted something simpler, something more syntactic. Then we had a look at programs, how programs actually work. What you see on the top of this slide, it's the session type for the server that we have seen before. I've just made it a little bit more interesting. I made it recursive, right? So this mu t, so you start a recursion, and then when you see t at the end, it just calls back the recursion. It loops over and over again. And then I implemented it with Go programming language. I added some prints and some operations to manage the time, to make sure that actions are executed in times that satisfy the constraints of the protocol. And then you can see in the bold face that there are the two interactions, the send of number 10 and the receive that and we will print. Okay, executing it on my machine, we observed an interesting pattern that you can see. We observed that the messages were received almost at the same time than when they were sent. Right? So you see there is a little bit of difference, but up to a certain precision, basically the receive action could not make arbitrary delays after a message was in the buffer. In fact, we want to disregard all the precision error as non-negligible, which is well, unavoidable when we talk about models. Okay, so we have observed that when you look at receive primitives may be blocking, maybe non-blocking, but when a message arrives in the buffer, they return immediately. They don't have this arbitrary wait. Right? So the classic semantics that we have seen with session types and was also taken by the literature of communicating timed automata, of communicating automata with time, is general, which is good in general. But for our purpose, if we can restrict the semantics a little bit, then maybe we can find some interesting properties. And we can restrict it in a way that makes sense, that reflects our problem at end, our receive primitives that we want to consider. So we defined another semantics, less general, that we call urgent receive semantics, in which messages are received as soon as they are in the queue, as long as the constraint, the time constraint is verified. So you may have some wait if the constraint is not true yet, is not satisfied yet, but as soon as the constraint is true and the message is in the queue, the receiver needs to receive. Okay, this makes execution a little bit more synchronous with respect to the classic semantics, but as asynchronous as the executions that we have observed with common receive primitives. Okay, and we have shown that with this specific semantics, the problems that we have observed in the previous slide don't occur, and in fact, if we put a session type in parallel with its dual, their combination, their composition enjoys progress, namely it's feasible when using urgent receive semantics. Now, some of you may have an objection with that. I got these objections a number of times. Well, asynchrony is all about network latency. We are talking about distributed systems, right? So now I'm executing this program in my machine, but what about nodes on a network? This objection is very valid, and we will tackle this later, where we can encode these network delays at a later stage. Okay, so we have looked at interaction structures and seen that we need to take a bit care in order to have correct interaction structures that can be easily implemented in a distributed system. Now, how can we then bring these properties to programs? Now, I will not look at programs as such, but at abstractions of programs. And we abstracted programs using a calculus. Now, a calculus may look unfamiliar as a syntax, but every primitive in the calculus is actually representing some primitive that we are all familiar and we see every day. So I'll make an example of a system in the calculus. The one you see on top there is a system where you have a session. The session is defined by this new AB. AB are two channels that are private to the session. They are the two endpoints of a session between two participants. And the two participants are PS and PC. And then you have two queues, the queue from the endpoint A to endpoint B, that is 0 and is empty, and the queue from B to A that is empty at the moment, but you can then add messages, right? And earlier on, we have seen some pseudocode that implemented the server that receives an integer and replies with a string and its corresponding client. Here you can see the corresponding version by using the calculus. It's very similar. It looks unfamiliar, but it's all, well, the same stuff. You don't have print statements. You don't have anything that has not to do with communication. So in the calculus, we want to keep things minimal. Right. On top of that, we also want some primitives that model the flowing of time passing. And there are two ways in which time can flow. It can flow internally, so you can have sleep primitive, or you can have the invocation of a function that is time-consuming functions. And these are all modeled with a delay delta primitive. Delay delta is a primitive that, sleeps, takes some time within an interval delta, and then continues as the process P. And so these are internal delays. And then there are external delays when we are waiting for a message that is not arriving yet. And this is the last one that you can see there. The last primitive of the calculus is a receive action. On a channel A, we are receiving a message B. B then is bound in the continuation P. And N is a parameter. And with this parameter, by setting this parameter, we can represent a wide range of received primitives in the real world. If we set n equal to 0, we have a non-blocking primitive. These primitives that look in the queue, want the message immediately. If the message is not there, throw an exception. We can have a blocking primitive, the primitive that remains blocked forever until the message is received. Or you may add a timeout. You can set n to any whatsoever real, and then you have a primitive that if the message is received by the timeout, then continues as P, otherwise throws an exception. Let's make an example. So, let's look at a snippet of the SMTP specification. A server should have a timeout of at least 5 minutes while it's awaiting the next command from the sender, from the client. A protocol using session type that satisfies this constraint is the pair that you see on top, S that receives a command when X is smaller than 5 and resets, and the corresponding client. And a program, the simpler program you can think about, well, I could think about, is a session where you have the sender that sends immediately and the receiver that waits for a timeout of 5. You see the receive primitive with timeout 5 and then continues. Of course, you cannot assume that the sender and the receiver make their implementation by talking to each other. So we have session types, and then you need to drop any assumption on any knowledge on how others may implement their endpoint except the type. So you would not know that the sender sends the message immediately. As when you make the server, when you implement the server, you need to be general with respect to the type. Other examples of implementation is one in which the server does something for 4 minutes and then has a receive primitive with timeout 1, and the receiver has some delay. Or one in which we really want to use the non-blocking primitive. We want to use A with the timeout set to 0. So we wait almost until the final deadline 5. So we wait for 4.9, and then we receive immediately. We want to receive immediately. Okay? And yeah, all of them are correct except the last one. So the last one gives some problem. Can you see why at a glance? Okay. Not all timed programs that we can write are time safe. So I will show you what can go wrong with the third option. Okay? We have seen, so the server is specified as a session type on top, and we have the implementation with the non-blocking receive there. The client doesn't know how the server is implemented and may decide to wait just a little bit longer than 4.9 before sending a message, right? This would go into a state in which the server needs to receive now and the client wants to send a little bit later. And this brings to a failed state. Okay, so this is not a good implementation of the protocols. Okay. So we want to provide some mechanism that not only checks the well-structuredness of the implementation, but also check its time safety, checks that time constraints will not be violated. Okay. This is done by algorithms that implement a typing system. I will not go into the details, I just want to give you a glimpse on how it works. So you have a typing environment and a program, and then you have rules by which you compare a typing environment with a program. Here you can see the rule for the receive and send. There are implementations then of these typing systems. There are several in literature. This is a non-exhaustive list for Haskell and OCaml. So there are two things that are done by these rules. The first one, checking the data types. When a message is sent to received, you need to check that it's of the correct type. And then you have to update your typing environment accordingly. But also, what is different from normal type checking, you want to check that when you have a receive type on a session A, then actually, yes, on that session, on the endpoint A, you are doing a receive, so you are matching the protocol, and the same for the send action. Okay. I'd like to go a bit faster here. So when you want to check also time constraints, you need to extend the typing systems as we have seen it. And the extension includes this V that you see. So on the left-hand side, you have an environment. You have a session A. And then the session not only includes the session type, but also a virtual clock. The virtual clock tells you what is the value of the clocks at that point. Right, so you can compare it and check that when a message is sent or received, in that case received, you need to check that is correct with respect to that virtual clock. Now, I will not go into the details. I will just show you why it is, how it is captured that the implementation we have seen of the delay and the non-blocking primitive is not correct. I've spared you a number of details of these rules, but there is one specific constraint when you check a receive action in which you want the process, the receiving process, to be receptive when you have a deadline up to the last deadline. So you may restrict the interval in which you are listening on a channel. If you have a constraint, you need to be listening for 5 minutes. You may start listening a bit later, but you need to be ready to listen when it is the last deadline, because otherwise you may miss messages that come after, right? And this was not satisfied by the process. So all what I wanted to say here, you have some typing rules that scan the process and compare it with the open sessions that these programs are implementing. There possibly are many sessions in parallel. And we also added a virtual clock to also check the correctness of the timing of the interactions. Okay? Now, I go back to this objection about asynchrony and network delays. And I mentioned that we can encode them, and we can encode them by using the process, the calculus. So one way in which we can do that, so let's see a simplified version of the snippet of SMTP where I have omitted all the continuations. We can encode a network latency using forwarders. So we can put some process in the middle just for the sake of type checking, and this process will model the network latency. For example, you may have, you see the blue is the server, the red is the client, and the black is the forwarder that takes a message from the client, delays for at most 1, and then give it to the server. Okay, this forwarder is modeling a network delay of at most 1 minute. And we can check that, well, the process is robust to network latencies of at most 1 minute. If we have a network latencies of at most 6 minutes, then this is no longer the case. Okay, quick wrap up. We have seen in the first part of the talk that asynchronous communication is complex, and with time even more so. But we have seen that by structuring appropriately communication and by looking at the appropriate semantics, we can ensure that protocols behave correctly. There is an issue of expressiveness there, since the decidability of properties in the asynchronous scenario it's a fact. Well, all the solutions that I gave you are not complete, so they all rule out protocols that are correct. This is unavoidable. For example, remember that session types do not model mixed states, right? States in which you have a send or a receive as an outgoing edge. And the first time I saw this constraint, I thought it was very reasonable because, of course, in a distributed system, you don't want to create confusion of who's doing the next step. But can you think of a scenario in which actually mixed states are good? A case in which you may either send or receive while you are doing a program. Timeouts. right? Timeouts, you may have a server that says, okay, I'm waiting for 5 minutes. If you send me nothing, then I send you quit, and game over, okay? And so it's a bit sad that we don't have timeouts. This is ongoing work. Second part of the wrap-up. When you want to pass from correct protocols to correct programs, you can do this by using static verification, static behavioral typing. Static verification relies on models, on predictions, on how timing or how systems will behave at runtime. Okay? And runtime behavior may differ from the predictions. So, we all know that people are late sometimes, and delays that are unexpected may happen. So we work under the assumption that the real programs follow predictions with negligible jitter. But if we are really worried about jitter, then we need something else. So we need something to increase robustness of our verification method. And one promising way forward is to look at a hybrid approach in which you use session types to inject runtime instrumentation into programs in the form, for example, of exception handlers. And these exception handlers can be as simple as defining alternative path, or may also be adaptive and then maybe rearrange the protocol in a way to catch up when the program has wasted time before. But this is all work to be done. And with this, I conclude my talk, and I'm happy for any questions. Repeatedly, you can ask more questions or conclude.